Okay, we are back with the last exercise where we'll be putting everything together. So I would ask all of you to open now exercise 4. So we've learned so far how to model the plane of array irradiance, how to model the PV array power, and the inverter power. Now we'll need to put all of these together, and our inputs will only be the solar irradiant components. But when modeling a PV system, so in addition to the data sheet of the panels, the data sheet of the inverter, the input irradiance, temperature, and all that, we also need to find out or assume or estimate what are the losses that occur from the photons reaching the front surface of the panel to the electrons reaching the electrical power grid. And there's various loss mechanisms that can occur as the energy transforms and flows from as it's converted from photons to electrons and it's reaching the electrical grid. So the first type of major losses that can occur is that you have horizon shading losses. So you have buildings, you have mountains, you have trees around your PV system that is blocking some of the sunlight. And this is particularly important for rooftop applications in residential areas because you'll always have some kind of buildings and trees around. And if you are designing your system only using satellite data or data from PVGIS or Meteonorm, those don't really account for horizon shading losses, at least not for the ones close by. PVGIS might account for if you have like a really large mountain like you guys do in Réunion, but it will not account for houses and things like that. So for heavily shaded systems that are located in in urban areas, you need to account for horizon shading losses, and these can be modeled either using a 3D model, or you can use a tool like a solar pathfinder or the SunEye that measure basically an image of the sky. It has this 360 camera or 180-degree camera, fisheye camera that measures the sky and can determine the skyline or the horizon line where the buildings are and estimates what are the potential horizon shading losses. And then you need to account and basically derate your DNI and DHI using these horizon shading losses. Now, once you have these, you have the plane of irradiance, and from the photons reaching the surface of the panel up to the electrons coming out of the panel, you can have a number of loss processes. And we group these in two rough categories. The first category is capture losses, and the second one is thermal losses. Thermal losses are quite easy to understand. It's decreasing with efficiency as the temperature increases. And those are relatively easy to model using a PV panel model or using even the temperature coefficient. These are the thermal losses, basically. So here we just need to estimate what the cell temperature is. We know the kind of the temperature coefficient or thermal loss coefficient, and then we can estimate these losses quite accurately. It is more difficult to estimate the capture losses, and because those depend on a number of things that can happen to the panel. So first of all, soiling or snow, depending on where the panels are installed, can partially block the sunlight for parts of the year. How much they block really depends on the tilt of the panels, how much pollution is in the area, how often it rains, and so on. So There are some models. There's also measurements, soiling measurements, so snow measurements that you can use to estimate these factors. Most often they are used as derating factors, either yearly or monthly factors that you apply. That's the, let's say, the easiest way that they are applied. But like for more accurate simulations in heavily soiled or snow areas, then you need to use a model. Then you have the reflection losses that we've talked about, which depend on the angle of incidence and the type of glass. You have the aging that we saw, that if you have older panels, you need to account for the degradation. Now the degradation rate, 0.5 is just the average one. It might be higher, it might be lower, depending on the quality of your panels and the operating conditions. So you'll need to either try different degradation rates or look at similar systems in the area and or read the literature on for the specific climate that you have, what's the degradation rate. It also depends on the type of solar cell. So thin films usually degrade faster than crystalline ones. Then you have kind of also adjacent to aging is other failure mechanisms that degrade the panels beyond the assumed degradation rate. And that can happen. Panels fail, solar cells fail with time, and these might affect just some of the panels or some of the arrays. So you need to be aware that that can happen. Then you have some of these bit more abstract ones like spectral losses, mismatch losses. So if panels degrade at different rates, the voltage and current will not match with each other anymore, and then the MPP power tracking will not be optimal, and you have overall a lower efficiency of the array as opposed to the efficiency of the individual panels. Then you can have losses in the diodes as well, because they have a voltage loss as well. Some of the panels, older panels, used to have lower efficiency at lower insolation, and also as panels degrade, especially through PID or shunting type degradation modes, their efficiency might no longer be constant. So they might have one efficiency at high irradiance and another one at lower irradiance. Or you can even have near shading. So something that is not soiling, maybe some vegetation, maybe something else on the surface of the panels that is blocking the sunlight. Now, you can also have losses between the panels and the inverters, and these are cable losses and string diode losses. These can be modeled if you know the length of the cables, the thickness of the cables, the current rate, the current that passes through them, and the material of the cables. Then conversion and clipping losses we've discussed. And then for especially utility scale systems where you have long AC cables and transformers, you also have some losses there. So we've learned how to model individual components. Now, when we model a system, we need to be aware that these factors come into play as well. So we'll need to model them. So we'll start with an example of modeling a single inverter system. So we'll model for inverter 1. Our input will be the measured weather station component, so DNI, DHI, and we want to estimate what is the AC power output of inverter 1. So basically putting all the models from the 3 exercises together and see how accurate can we model inverter 1. So let's start with this one. First step will be to initialize the environment. Then the next step will be to define the system parameters. in a similar way that we had. So the tilts, the degradation rates that we determined. We'll need to model both input 1 and input 2. And if you remember, for inverter 1 input had 36 panels, 1 only had 18. So we'll need to model the DC power of both of these, then model the inverter, and then estimate the AC power. So this is all the parameters that we need to define before we can develop any of the models. So, and then we'll first do a simulation for the October data set, and then in the later task, we also have one for the full year. So we'll define the system parameters, then the losses. In the previous exercise 2, I showed you one way to calculate the losses, at least the aging losses, using this equation here. Now pvlib has a way of accounting for these losses through the pvwatts losses function, which is basically calculates a loss factor where you need to specify individual types of losses that you need to assume in some way. Now, for our system, there's no soiling and shading losses or snow losses, and we assume the mismatch and everything else is 0, because most of it could account very well through the degradation rate. Now, we only kind of adjusted the losses for a single day. So if you want to be more accurate, then you need to do maybe a system level analysis to see if there's if these degradation losses, maybe the degradation rate is lower. So some of the other losses are distributed as for sure there will be some DC losses or things like this, or LID losses that could happen. But for this system, we can define the aging losses using the PV loss factor by adding them to the age loss property, where we multiply the degradation rate with the operation years. And that proved to be accurate enough for our purpose. Then we'll import the weather data like we did previously. And then we'll put together all the models for modeling the effective irradiance. So to model the effective irradiance, first we need to model the POI, the plane of array irradiance. And for that, we need the solar position, we need the angle of incidence, we need the IM losses. And then usually when we model the plane of array, we also model the temperature, cell temperature. So we put everything together in a single function, for which we provide the rate, tilt, azimuth, time, solar irradiance components, air temperature, and wind speed. And this calculates basically everything from exercise 1 and 2 and returns the effective irradiance and the cell temperature. And in this way, I can reuse this function in several places without having to repeat the code. So I will load this function, and then for inverter 1, which is located on the northeastern rooftop, I will model the effective irradiance and cell temperature for the October data set like this. And then here's just some plots to check what we are plotting, if it makes sense. So with a single function here, I can model both effective irradiance and solar cell temperature just from the weather components and the time vector of the data set. So now I have the effective irradiance and solar cell temperature. Now I can model the DC power and I model the DC power using the PV watts function, where I provide effective irradiance, cell temperature, rated power of each of the strings, and the temperature coefficient. And then I applied the derating factor to this vector. And then I made a number of helper functions that help me plot different things, which you'll see in a bit. So for the DC power of MPPT1 and MPPT2 of inverter 1, we'll model it and see what we get. And then we compare it with the measured DC power for this inverter. And we can see for MPPT1, the model measured matches very well, and similarly for the MPPT2. We can see that since MPPT1 is a larger system, so this is a 36 modules or of 7.56 kilowatt peak. We also have a higher power output during the day, whereas this is about half, which corresponds to 18 modules and 3.78 kilowatt peak. And then these two functions here, one plots a single day and compares basically a modeled power with a measured power. And the other one, the daily plots for each day how much energy the two arrays have generated in kilowatt hours, measured versus modeled. So this is just basically I put the plotting code together so that I don't have to repeat it, because I have 8 arrays that I would need to compare. So if I make it as a function, then I can just reuse it in different places. And then you can have a look at the actual code here if you're interested. Then for the AC power of inverter 1, I use the PV watts multi, where I apply the estimated power of the two MPPTs. And then when I run it, I get basically the modeled inverter power versus the measured one. And the only inputs to the system are the weather data and the weather data, basically DNI, DHI, GSI, wind speed, and temperature. And then here you have the model versus measured daily energy on the AC side, as well as the total energy for these 2 weeks. Now, task A, we'll do it very fast together. In task A, basically, I will leave you to do task A, and then we'll do task B together. So for task A, you need to do the same thing, but for inverters 2, 3, and 4. So very similar. You'll need to calculate the rated power of the array. There's a second inverter there, which has a slightly different efficiency and rated power. You'll need to define the losses, and there are some inverters for which the losses are not the same. I think some of the PV arrays are slightly degraded, and then you'll see some differences. Then you'll need to calculate the effective irradiance and the cell temperature for the south arrays as well. And then for each of the other 3 inverters, you need to calculate the DC power, the AC power, and so on until you get to the 4th inverter. So I will let you do this for 15 minutes. And I think we'll go through the solution together after that. If you have any questions, now is the time. Okay, let's have a look at the solution together. So we have the other three inverters, inverter 2, 3, and 4, that we need to basically put together the models and parameterize. So first, we'll need to define the rated power of the remaining 6 PV arrays connected to inverter 2, 3, and 4. And we can see for inverter 2, it's 18 and 18. So we have it here. And then for inverter 3 and 4, it's 36, 36 per MPPT input. So 18 times 2. And for inverter 3 and 4, these are the 16.5 or the 15.75 kilowatt rated inverters. So we'll need to add those as well. Then we'll need to assume the losses, and we'll start just with the degradation. So we'll put everything to 0. We'll just account for the degradation now, and then we'll adjust as we go. So I'll add this there. Then I need, for the inverter 3 and 4, I need to model the efficiency, the effective irradiance and solar tail temperature. So I'll call the model irradiance function that I made previously, just with the parameter specific to this array and for the data set from October 2022. Then I start inverter by inverter, and I'll see what I get. So if I start with inverter 2, MPPT 1 and 2, I can see that MPPT 1 looks good. Modeled versus measured at around 3 kilowatts for a clear sky day, it looks very nice. This one, not so much. They both have the same degradation rate. So something happened with the second array of inverter 2. Now, unless I go on site and determine what happened, so what could have happened? One possible thing is maybe some panels were removed, or they are damaged or short-circuited, or maybe some panels are more degraded than others, specifically to this inverter. So something has happened that caused the whole array to generate less power. So unless I go there and see specifically what's happening with the system, I cannot know. The only thing I see is the degradation is uniform, or the reduction in power is uniform. It's not a shading kind of thing. So what can I do for this one? It's basically the rated capacity of the entire string has been reduced. So to account for this specific array, so on MPPT2 from inverter 2, I can account for additional power reductions in addition to the degradation rate or the aging by adding a nameplate rating loss. And by trial and error, I arrived that for this one, a nameplate loss of 8% has occurred. The specific reason I don't know until I do a diagnosis of the array. Could be degradation of some of the panels, could be short-circuited bypass diodes, or maybe at some point somebody took down the panels because they were damaged. We don't know until we go there. So, but in order to model for that, you use the nameplate rating loss factor. And then your modeled and measured power coincide much better. Then I do the same for the AC power, and I get good correspondence, and also overall daily energy correspondence as well. Then I move on to inverter 3. I do the same. And I see that for inverter 3, there's a little bit of difference in power here. So I could, in principle, account for this as well with maybe there's some additional degradation here. I could put here 1% in nameplate loss for array 2 from inverter 3. So if I go back here, when I run the simulation, they match a little bit better. Then I run the AC simulation. There's still a bit of difference, so maybe there's some additional losses there I would need to account for. So that I have not. So maybe there's some availability losses or things like that that I should account for. For now, we'll say it's good enough. And then we do the same for inverter 4. This one matches very well. And on the AC, it matches very well. So now I have made models for all my inverters, and then of course you can tweak the loss factors a bit more. You can, choose several days. If you have a longer data set, you can also try to adjust them so the actual energy matching is better. So right now I made my energy matching based on a single clear sky day, but you could tweak your loss factors based on the daily energy such that the measured and the model coincide a little bit better, which they don't do that well for all the days here. They do very well for this day that I've chosen, but maybe some of the other days not so well. So they could do with a little bit more tweaking, which you can do on your own if you want. So this is one way to do it. So part of modeling the entire system is actually tweaking the loss parameters. And the more understanding you have of the actual conditions of the system, if you've been on the site, if you see any soiling, if you see if there's shading, if you have some kind of understanding of what's happening with the panels, then it's a bit easier to guess or have a good estimation of which of the loss parameters have changed, and then try to adjust those. Okay. Then we've reached kind of the last part, which I will let you do by yourself at home. I'll just introduce this this exercise. Basically, you have models of all 4 inverters that you've tested for the 2-week period. Now you will use those models for the 4 inverters for a full year period, where your input data set will be the Meteotercent, which has the weather data, and your validation data set will be a 4th data set that we haven't used yet, which is it's actually not this one. It's this one, Sunzel. This is measurements for 2 years for the system, and then we select only the 2nd year. So this Enerpulse data 2022. Now this data set does not contain plane of array irradiance and MPPT measurements and all that. It contains only total AC energy and total DC power. So these are the only 2 columns contained in the data set. So it's a bit less information, but it's for a longer period. So what you need to do is use the weather data from 2022 together with the models that were developed in task A and simulate how much power the total system. So if you add up the AC output of all 4 inverters and the DC input of all 4 inverters, they should coincide more or less with the measured power for that period that you can find in this data set here. And the data set is already prepared for you. There are some days where irradiance is missing, and this is what happens in reality with PV systems and SCADA systems. Unless you have a personnel on site and a very tight maintenance schedule, SCADA systems break and there's data missing. So you'll see for the actual measured data, there will be some days missing in March and February. But that's fine. You can still do the comparison on day level or month level. So we'll leave this for you to do at home. You also have the solution to this one in the solutions folder to help you along. And I will close this session with a short quiz, which I'll display. I'll copy the link and give you the link in the chat. And we'll just have a short quiz. So the first one, what are the factors that affect the effective irradiance? Is everyone else checked out for lunch? Am I talking to a wall?
No, it's because it takes a while when you copy the link to the chat and for the link to be displayed. And it seems for Philippe it doesn't work. It works for me, but not for Philippe.
Okay, we have a technology thing. But then let's skip the quiz. I think Mathieu, you have some closing things for the students. Should I pass it on to you? Or should we finish with the quiz?